Welcome to AI Podcast. Today we're digging into a NeurIPS paper called T1, all about teaching AI agents to plan with tools over multiple turns.
The quick takeaway first, please. What's the one sentence that matters?
T1 is a new data set and benchmark that tests whether language model agents can plan a sequence of tool calls across a conversation, reuse what they already found using a cache, and adjust the plan as the user changes their mind.
So not just answering once, but thinking a few steps ahead like a good travel assistant. Who's behind it?
Led by Amartya Chakraborty with collaborators at Capital One, and another name you might recognize is Genta Indra Winata. It's presented at NeurIPS 2025.
Got it. Why did they build this in the first place? Don't we already have tool use datasets?
We do, but most focus on single turn or single tool actions. Real assistants work over several turns, juggling dependencies. Think of planning a trip. Your hotel check-in depends on your flight arrival, your dinner time depends on both, and you shouldn't redo every search from scratch each turn.
Right, you'd keep notes. That's the caching bit, yeah?
Exactly. T1 bakes in a short and long-term cache so an agent can decide whether to reuse earlier results or recompute. It's like the agent's notepad in memory.
What's actually inside T1?
About 13,500 dialogues, all framed as conversations with a travel assistant. There are 9 settings, 4 single domains like flights, hotels, restaurants, and attractions, and 5 multi-domain mixes like flights plus hotels, or the full flights, hotels, and restaurants combo.
And the agent uses tools?
14 of them. Some are domain tools like search or filter for flights or hotels. Others are utilities, including saving to cache, retrieving from cache, sorting, and a simple helper to adjust dates or ask the user for missing info.
So the agent isn't just talking, it's generating code to call those tools, right?
Right. The reference system, called T1 Agent, converts each assistant turn into executable Python that invokes the right tools with parameters. The code runs in a sandbox, and the results get cached.
That makes evaluation cleaner. You can say whether the agent called the right tool with the right arguments and whether the code actually ran.
Exactly. The paper evaluates several things at every turn. First, tool choice, meaning did you pick the correct tool or combination? Second, parameter matching, did you pass the right inputs? Third, code execution, did it run? There's also an information-seeking score for how well the agent asked for missing details, and a check on whether its cache summaries match what they should be.
Before we go deeper, give me a concrete example. Picture I say, find me a flight to Chicago that lands before 3 and a hotel near the Riverwalk.
The agent should first call flight search, maybe filter by arrival time. It then saves that flight list to the cache. When you ask about the hotel, it shouldn't research flights. It should pull from cache to figure out the check-in window and location, then call hotel search, then filter by neighborhood. If you change the arrival date, it should realize the cached hotel options might no longer fit, so it recomputes where needed, but keeps any still relevant pieces.
Nice. What about where the data comes from? Is this live web data?
No, it's a controlled knowledge base built largely from U.S. cities and airports, with some synthetic names for hotels and restaurants. That avoids leakage from the model's prior world knowledge and keeps the evaluation reproducible.
Makes sense. Now, what did they actually test?
They ran a mix of open weight and proprietary models. One interesting result is that a smaller open model, fine-tuned on T1 style behavior, beat much larger untuned models on several metrics. That's a strong signal that task-specific adaptation matters for tool planning.
So brains plus practice, not just brawn. How about the closed models?
On a smaller comparison split, leading proprietary models generally remain ahead on overall tool and parameter scores, but the fine-tuned small open model held its own in places, especially on the cache-aware behavior.
That cache point keeps coming up. Why is it such a big deal?
Because multi-turn assistance is expensive if you recompute everything. T1 tracks whether models save, retrieve, and actually reuse prior results. Models that show disciplined cache use tend to complete tasks more reliably and faster within the simulated environment.
What about prompting style? Did they just let the models figure it out zero shot?
They tried different in-context example counts. Zero shot struggled, a few demonstrations helped a lot, and then the gains flattened out. So a little guidance goes a long way, but more isn't always better.
And multi-domain versus single domain?
Multi-domain is clearly harder. When flights and hotels interact, or when you add restaurants on top, errors compound. It reveals weaknesses that don't show up in simple one-tool tasks.
Are there any caveats we should keep in mind?
A few. The scenarios are US-centric, and many entities are synthetic, which keeps things clean but less messy than the real world. The domain scope is mostly travel. Also, some evaluation pieces like the quality of information seeking rely on text similarity metrics, which don't perfectly capture whether the question was the right one, and results can be sensitive to prompt design and decoding settings.
Right, the usual fairness question for benchmarks, but it sounds like they worked to make it reproducible.
They did. Code and dataset are released, and they document training, inference, and hardware details so others can replicate.
I'm thinking about how a practitioner would use T1 tomorrow. What's the practical angle?
If you're building an agent that calls APIs, T1 gives you a sandbox to test three things. First, can your agent figure out which tools to call in the right order? Second, can it gather missing inputs by asking sensible follow-ups? Third, can it remember what it just did and avoid doing it again if nothing changed?
And if I wanted to squeeze more from a smaller model?
Fine-tune it on T1-like traces. The paper suggests that targeted fine-tuning beats scaling up blindly for this kind of planning. It also hints that encouraging the model to think about memory and dependencies pays off.
Let me push a bit. Suppose I'm skeptical. Could the results shift if we used live airline APIs or non-US cities?
They might. Real APIs introduce variability, latency, and occasional failures. That's a great next step. Broader geographies, live data, and more domains like calendars or rideshare so the dependencies get even richer.
And maybe rethinking how we judge information seeking, not just matching wording, but checking if the question is necessary and helpful.
Exactly. Human preference judgments or task-grounded correctness would complement the automatic metrics.
All right, quick recap for listeners. T1 is a multi-turn, tool-focused benchmark in a travel assistant setting. It stresses planning across tools, using a cache wisely, and adapting as the conversation evolves.
The headline result is that small, fine-tuned models can outperform much bigger, untuned ones on core planning metrics, while top proprietary models still lead on many scores. Few-shot examples help, multi-domain is hard, and cache discipline correlates with better outcomes.
Strengths include executable ground truth, clear turn-by-turn evaluation, and a realistic emphasis on dependencies and memory. Limitations are the synthetic, US-heavy setup and some metric choices.
And the forward path is broader domains, more realistic APIs, richer evaluation of questions an agent asks, and deeper studies of memory strategies.
Perfect. If you're building agents that have to plan, decide, and remember, T1 looks like a solid proving ground.
That's our show. This is AI Podcast. I'm Ethan.
And I'm Maya. Thanks for listening, and we'll catch you next time.